It's disappeared again.
No, come.
Let's come back.
Come. Over to you, Anthony.
Fantastic. Thank you very much for inviting me along. Really appreciate the opportunity to talk to you. As Alberto has said, I've written a number of books about the London Underground. It's something I've been interested in since I was about 15, and I did a project for my social and economic history GCSE. And the odd thing is it's not actually my profession at all. I work in cybersecurity. This is just a hobby for me. But as my wife says, you know, it's a hobby that actually pays. I get to sell books. Most people's hobbies actually cost them a load of money. So she's onto a winner there anyway. I'm probably in the way. I have to keep walking back and forth. I tend to walk around a lot when I talk anyway, so hopefully I won't be too distracting. So the background to this is a book that I wrote back in 2014, was published in 2016, called Building London's Underground. And the history to that was I've always been really interested in the engineering and the social side of the underground and railways in general. So hopefully, if you're all members of the PWI, you're interested in the engineering side of it rather than the train side of it. The trains tend to leave me really fairly cold. I'm interested in how do you build this huge infrastructure? How do you get the tunnels in the ground and so on? And so I bought a book about 2013 called Working London's Underground. It had a big picture of people working in a tunnelling shield on the front of it. And I was kicking myself saying, I said to my wife, I should have written this book all about how it was actually built, because no one's done a proper engineering history of it. And I read the book and it was rubbish. Apologies if any of you have read it and think it's good. It was just yet another 150 years of the London Underground book published in 2013. And it had a little bit about people working on the underground. There's really nothing in there about building it that was any above and beyond anything that had been previously published. So I thought, aha, here's an opportunity. I happened to have some months free at the beginning of 2014. And so I just hit the archives like mad. And I wrote pretty much all of Building London's Underground in the space of about 4 to 6 months. Then spent about another year finessing it, got the book out in 2016. And the amusing thing was I sent the synopsis to my publisher, who sent it off to a few reviewers to say, should I publish this book? And they all came back and went, we love a copy of this book on our bookshelves. It'll be fantastic, because they were all authors, but you'll never sell any copies generally. You shift a few tens of copies of it, so it's not worth it commercially. My publisher went, Capital Transport, said, well, actually, I'm going to take a punt on this one. I think we can sell it. And so we did a print run of 1,000 copies, and they all sold in under 12 months. So I thought that was a bit of a success. And I then realised this was end of 2016 by this point, and there's a lot more going on the underground. So we've had the rebuilding of Victoria Station, we've had the rebuilding of Bank Station, we've had the Battersea extension, and the little known one is there's a new tunnel being built at Euston for the Northern Line substation. And I thought, right, I'll write a new chapter to stick that on the end of the book, because we've sold all these copies, we can now sell more of them, but a larger edition. COVID came along, I was completely distracted writing a different book, and then my publisher said, well, actually, I don't want to do an expanded edition of Building London's Underground, because the people who will want to read the new material will probably have bought the first book and will be aggrieved now, with paper prices having risen, having to pay £40 for a copy where 90% of the content is stuff they've already owned. So I said, fair enough. How can we use the content that I've pulled together here? And I went and found lots of interesting new photos that, as far as I can tell, have never been published before, and linked those together. I wanted big photos, big captions, and slightly different focus. So the new book is focused entirely on building the deep tube, the circular tube tunnels deep in the ground. And a manuscript for that has actually gone off this week. So now I'm trying to work out precisely how to finesse that with the publisher. So that's the background to this. So I'm talking about deep tube. So the first thing I'm going to do is talk about that. So there are also tunnels and the covered ways that you'll find on the shallow tube. I'm not going to call it the tube, it's the underground of those bits. They're not tube tunnels. I don't care if they call it that tube as their brand. I'm going to be engineering correct here. So we've got the 3 types of them. So there are tunnels just below the ground that have been bored as tunnels. They've been mined out without disturbing the surface. The majority of the subsurface parts of the underground, so the Met, Hammersmith and the City, Circle and District lines, are built as covered ways. I'll explain that again in a moment. And then the rest of it is tube tunnels, so deep level circular tunnels, mostly cut out of London's clay. So here's where it all began. So back to 1825, Mark Brunel, father of Isambard Kingdom Brunel, who probably eclipsed him to an extent, created the very first tunnelling ship. So this was used to create the Thames Tunnel, which is now part of the London Overground beneath between Wapping and Rotherhithe stations. He had been imprisoned for debt, and while he was in prison, he saw a shipworm eating through a piece of wood. And the shipworm, Teredo nivalis, has two hard shells on its head that it uses to rasp a hole in the wood. And it gave him an idea that if you could support the clay or the material for which you're tunnelling continuously, you could construct a tunnel through ground that you wouldn't normally be able to build through. And his solution was this tunnelling shield. It doesn't look much like the tunnelling shields that we use to build tube tunnels. But firstly, it's rectangular, and it's a little bit ad hoc. Basically, it consists of 36 cells, so 3 rows of 12. I'm quite showing all of them here. Each one of which contains a miner and is an independent iron frame. They all fit together in this big rectangular block. And the front of it, you can just see here, there are lots of wooden boards. So on the right-hand edge, people who can't see me pointing very well, the right-hand edge of it, you can see all these wooden boards, and that's holding back the tunnel face. And each of these miners is standing in there, lit possibly by a candle, but not much more than that. So you look at this drawing, oh, it's really clear to see. They couldn't see what they're doing, really. What they do, one by one, they take a single board out, they scrape away the stuff in front, and this is not going through London clay for the most part. This is going through the rubbish at the bottom of the Thames. They thought they were going through subsoil, but actually the rubbish that accumulated in the river went deeper than they thought. And by rubbish, this is Victorian times, there's a heck of a lot of sewage basically down there. So it stank, it's pitch black, and they're basically taking a board out, scraping about 4 inches of soil away, putting the board back in 4 inches deeper, and then moving to the next one. Once all of their boards have been moved forward, their bit of the tunnelling shield will be pushed forward into the gap. And once all of them have been pushed forward, the whole shield can be moved forward, and their load bricklayers would come and build a brick tunnel behind. So in cross-section, it's a great big rectangle with 2 horseshoe-shaped arches through it. I'm not going to dwell on this in a huge amount of detail. It's been written about all over the place. It took far longer than expected. It cost far more money than expected. It was built in about 3 different phases because the money kept running out. There were several inundations where dips in the bed of the river that were caused by things like ships' anchors dragging along, and they'd break into it, the water would pour in. Isambard Kingdom Brunel, who'd been appointed resident engineer by his dad at one point after the main resident engineer quit, almost lost his life during one of the inundations, and he was washed all the way back down to the shaft at Rotherhithe, and basically with people at the top of the shaft suddenly saw his body bobble up to the surface and dragged him out, and basically shook him to get the water out of his lungs, and he had to recuperate for a bit. But it succeeded. It built the first under-river tunnel in the world. The next type of tunnel is the covered ways. So these are your tunnels like Met, Hammersmith City, and so on. First one of these was designed to link Paddington Station, which was fairly remote from the rest of London at the time, with Farringdon. It's that line, which is now the northern part of the Circle Line, is a combination of tunnels. So some of them have been tunnelled through, particularly around Clerkenwell. Some of it is open cut, but the bits are actually built as covered ways. Most people think you take your street, you clear all the people out of it, you dig a great big hole, and you put a railway in it. You just keep building it along to get to the back. And now you've got a railway, so you've got a hole, so you stick the tracks in. There we are. You build the tunnel structure in there, so you put your tunnel invert in, you build the crown of the tunnel, nice and arched for a bit of strength, you backfill, keep it going down to put the road back, and you now have a tunnel. It's not that easy. That's what a lot of the books will actually tell you it's been built like. There's a big problem, and that's what's in the subsoil. So most of London's streets, particularly the new road, which is what the combination of the Euston and Marylebone roads we have today, already had stuff underneath. So we've got a pneumatic dispatch company tube for blowing posts through. We've got gas and water pipes. Most importantly, we've got a huge great sewer in the middle. If you go and dig a hole in the road and you rip all that out, there's a lot of grumpy people in the houses either side who are now, obviously not going to have electricity, but you've cut off their gas, so they can't cook. You've cut off their water supply, and you've cut off their ability to drain their sewage away. But actually, it's rather more complicated than that. What you had to do is you dug up the pavements at both sides and put a great big trench in. built those along as far as you needed to. You then built a new sewer or a new pair of sewers and plumbed all that in and had to connect it without being able to tell people don't chuck anything down the drain at the moment. This was done while people are using the drains. You're now left with a redundant bit of sewer in the middle. You dig a big hole in the road now, and then you construct a railway tunnel. One of the problems on that bit of line is they didn't actually bother building a tunnel invert. They just dug it down to the soil, put some footings in at the bottom, stuck a drain in, bit of hardcore, and built a railway on top, which means that the tunnel can shift around a little bit, which is fine as long as you don't run big, heavy metal things through it at speed that might shake it. It might be the problem. So a load of those tunnels have had to have remedial work done on them over time. So anyway, that's all about the tunnels I'm not going to tell you about. It's really quite interesting. I get really interested in all this stuff. What I'm going to tell you about is building a tube railway. And at its simplest, this is how you build a tube railway. This is a tunnelling shield. And the idea of this came about after the completion of the Thames Tunnel. Different engineer, a guy called Peter Barlow, who was building the Lambeth Bridge. And in order to build the Lambeth Bridge in London, he was sinking piles into the river that were cutting through the clay. An idea came to him one day: if I turned it round 90 degrees and push it through the clay horizontally, I could make a tunnel that things could go through, vehicles could go through it, people could walk through it. And with a pupil of his, a South African chap called James Henry Greathead, he put together the idea for this tunnelling shield. And it's really very simple. This is part of the end view of it, and this is a side cross section. So effectively, it's a fairly short steel cylinder. So imagine taking like a food can and just cutting the ends off it. You're left with a circle of metal. That's obviously going to be a bit flexible and squidgy, particularly if you've got lots of clay pressing around it. So what you do is you put a big partition through the middle of it, which is shown here, which has got a square hole or a rectangular hole in it. So that gives it its structural rigidity. At this end, you put some adjustable steel cutters. Effectively, they're just like a circular blade around the edge of it. And then you fit into the back end of it. It's a bit thicker than just the equivalent of a steel can, but here you've got a bit of structure there, and you've got, well, it's labelled on this diagram as a hydraulic press, but the original one was a screw jack. So you've got something here that can push backwards, and then you've just got a thin bit of steel sticking back here. What you do is you dig a hole in the ground, you lower this into it, and then your miners reach through this hole here with pickaxes and shovel out the clay. Once they've shoveled out enough clay that's in front of this, it doesn't have to be perfect because you've got these cutters on it, you put something to wedge it against, and it's a lot easier once you've got a bit of tunnel, because the bit of tunnel you've just built is the thing you wedge it against. But you wind your screw jacks, or you pressurise your hydraulic jacks, and you push it forward about 18 inches. Once it's been driven forward there, some of your miners are picking up the bits of clay that have fallen out as these cut forward and taking it through. The others winding those jacks back in and into this space. And you can see here's the end of the tunnel, these bits here. You've got this bit here, which is the length of one tunnel ring. You build a length of tunnel ring. And at no point is the clay exposed from above, so there's nothing that can drop down over you. And you just keep on repeating that. And you're moving along 18 inches at a time through the clay, and you build a tunnel at no risk of subsidence. Now, the problem is that once you've done this, this is cutting a slightly bigger hole than your metal tunnel rings are taking up. So you've also got to have some people trying to go on behind, filling the gap behind. Because if you don't, and they didn't originally, the tunnel subsides above it. And then the people who own the buildings above it get quite grumpy with you because it falls to the crack. And when they've started driving this forward, they actually used the compressed air. They had a compressor that could blow the grout through holes. So they made up a lime mortar and blew that through. The other thing is you're bolting together big cast iron sections. So these weigh a couple of hundredweight each. I also know what that is in metric, but I don't, because it's all coming from the original sources and they did everything in imperial measurements. So they're big and heavy. There's no lighting down here again. So the miners used to use a blob of clay they grabbed from the floor or whatever, stick it onto the peak of their cap, and then put a candle in it. So they'd each be working by the light of one candle, but they'd be trying to keep alight. You're driving this forward, you're trying to move great big heavy bits of cast iron, bolt them together, and also you need to try and bolt them really closely together so that there's no leaks. And then actually put some compound in that would cause them to rust together over time. It's really impressive. When these have been dismantled for bits of tunnel, where, on Battersea Extension, for example, where they broke into the Kennington Loop and they took out tunnel segments that have been in there since the 1920s, they're absolutely pristine. It's a very, very good environment for keeping it. There's no running water or anything that's going to cause the corrosion of them. So that's basically how you build a tunnel, pushing forward. So the first one of these, I'm skipping over the Tower subway. The first one was a tiny little tunnel that was built between roughly the Tower of London and sort of these days where the More London development is, where the old City Hall used to be. It's very small. The only bit of it you can still see, there's a cylindrical yellow brick box on the Tower of London side of the Thames that says London Hydraulic Power Company on it. And that tunnel was built underneath. It had a very tiny 12-person carriage that could be pushed back and forth using a rope. And this was before Tower Bridge existed. So people would pay a penny to travel through. There had two classes of travel, first and second. You paid 2p if you were first class. Didn't give you a better seat or anywhere different to sit. It meant you queue jumped the people who had paid their penny. It lasted until Tower Bridge opened, and then that was closed down, because why would you want to descend a staircase and then go through a very narrow tunnel? Because they'd removed the wagon by this point. Everyone had to walk through. It was lit by naked gas flames coming out of a pipe with holes in it down the wall. Teenagers used to go down there and would run along, knocking out all the gas flames, leaving everyone in the pitch dark. They got sentenced to hard labour for that. It was seen as being a particularly unpleasant crime. So the first real one is the City and South London Railway, which is now part of the City branch of the Northern Line. This was built as a twin tube railway, so we're starting to see the evolution of what the London Underground, the principles of the London Underground forming here. It's a twin tube railway, so they built one tunnel for each direction. It was originally going to run from Elephant and Castle to the City, which was a really stupid idea, because no one ever needed to commute between those two places, because the people who lived at Elephant and Castle were not city workers. It was a fairly run-down area even at that time. So before it was opened, the company got permission to extend the line down to Stockwell, where there were a load of city workers. They bored the tunnel through. They had to follow the line of the streets in London, because at the time, property rights meant that you owned, I can't remember Latin for it, you owned the land of your property down to hell and up to heaven. This is actually what the Latin phrase translates as. These days it's changed slightly, but the idea was you went under someone's property, you had to get an agreement with them that you could tunnel under it, which usually meant you bought the property, which is expensive. But the government said, we'll give you a free way leave to build underneath public streets. So that's what they did, which is why so much of the early underground has got really twisty tunnels in it. Like the Bakerloo line, you can see it, or you can feel it following the big curve under Regent Street. And if you go north out of Oxford Circus, you can feel it do the wiggle outside All Souls Langham Place. So they had to build it. This is the bit where it passes under the Thames. They built the staging in the Thames. So of course you're going to build a railway that no one else has ever done before, and you're going to go and do it by building a pier in the middle of the Thames and building it from a river rather than on land. Why would you do that? Because you don't have to pay for a work site if you do this. You can send barges up to take the clay away, so you're not having to pay people with horses and carts to drag all the clay away from some shaft in London, in the middle of the city, and land in the city is really expensive. And they wanted to build this bit first because they couldn't build the under-river tunnel. What was the point of building the rest of it? And Greathead, who was the engineer for this line, wanted to prove that he could build a proper working railway. So he built this. The other problem was that the original intention was it would be cable-hauled. It was going to use a system called the Halliday system, which is very similar to the cable-hauled cable cars, that, like tram cars in San Francisco. So it'd be a continuously moving cable through the tunnels, and the cars would clip onto it and be pulled through, which meant that at the termini, you'd have a single platform. The car would have to go in, detach from the rope moving in one direction, and then attach to a rope moving in the other direction to come out. It also meant it didn't matter what gradients you used. And so what you can see here is under the river, you've got two tunnels side by side, and as you head north, they swing round, so they're one above the other. This had advantages and disadvantages. So here, you sink one shaft down and it intersects both of your tunnels, so you don't have to build two shafts or start building side shafts out. So you sink a metal shaft down here, you build a great big block of brickwork, you then send four shields out simultaneously to start building the tunnels. The other reason for this is that if you look at the map, if you look at the map, here's the shaft. The shaft is just there. This is the staging they put up. here is Swan Lane and Arthur Street. So Arthur Street goes around a really nice 90-degree curve, fantastic for railways. I'm sure, particularly as the track engineering people, you'll know just how good it is to start sending trains around 90-degree curves. Swan Lane is really narrow. So you want to keep your tunnels under that, you have to stack them. There's no way you can put two side by side under it. So you build your two tunnels. Here you've got the station, so you've got one big tunnel, two platforms and a single track in between, spiral staircase and a lift going down to it. You really don't want to make this too deep. And it's okay because a cable's going to pull the car along. So it doesn't matter that you've built the curve, the track here in a tunnel that goes around a 90-degree curve up a 1 in 14 gradient. Yeah. It made it really difficult to get the trains in here because the cable company went bust in 1888, 2 years before the line was due to go live. And the directors went, I know, electricity, that will sort the problem out. There are no power stations in London at this time. So they had to go and build pretty much London's first power station to power the line. They've got to develop the technology of the electric train. So they went to a company called Badsey-Ellis Platt in Manchester, who put their best engineers onto it and developed a series of trains. And so I'm not going to talk about trains, I'm not really. They look like two upright pianos back to back with live contactors in them, pulling 3 carriages through the tunnels. The tunnels here are 10'2" in diameter, which is notably smaller than the current London Underground. And you've now got to try and get one of these trains being powered at 550 volts through this tunnel, up a 1 in 14 gradient, round a 90-degree bend into a platform and stop dead. You've already scrapped the idea of electrically lighting your stations because your power station can't produce enough power. It can only produce enough just to run the train service. So all your stations are now lit by gas. Your trains come out of Borough Station. The drivers have to basically chuck as much power into motors as they can, build up as much speed as they can, and hope they can get up and round into here. If they can't, by the time they're going up this hill, the lights in the carriages, which are electrically lit, have gone to a dull red glow. Sometimes it works, often it works. But every so often, heavily laden train in the morning, the train would get part way up, would stall, so the driver would then have to basically take the brakes off, roll it back down and have another go. If they couldn't, they then have to contact the signalman. The next train that's waiting at Borough to come in, they'd have to tell the driver, detach from your train, hook onto the back of ours and give us a push and try and get us up there, at which point they would then have to detach, whiz back, wrong line, to their train waiting in Borough, and then hope that they could get up into there by the time they'd pulled out. And if not, they'd have to ask the next train to push them along. What a way to run a railway. There's a lot learned from this. There's also some just terrifying engineering stuff. So, I mean, I go into tunnels and things and I'm decked out in steel-toed boots, full high-vis PPE, glasses, gloves, ear protection, all this kind of stuff. And when I've gone into the Crossrail tunnels, I've gone down in one of those Alimac temporary elevators in a shaft. There's a navvy descending the shaft into the City and South London Railway. Basically, there's nothing provided for the workers other than there's the tunnel that all the railway stuff is going in and all the clay is coming out. And you stand on the bucket that the clay will come out. So they'll drop you down in the bucket and then that will come back up with a load of clay that's going to be tipped into a barge. And as you can see, obviously complies with Network Rail PPE standards there. They did fall off. Things fell down the shaft and squashed people. It wasn't fantastically safe. How do you build a railway in tunnels, underground, following the line of the streets perfectly, when it's down there and you're 50, 100 feet above it? So I'm not going to dwell on this because it's all maths and trigonometry and it is in the evening now. We probably don't want to be doing that. But basically, down the road where you want to map your railway, you'd send a team of people along at night who'd put little brass pegs into the road directly above the centre line of the tunnels that would be going along. And then they would measure the distance between each pair of pegs for a tunnel and the angle using a theodolite. So you'd have everything mapped out perfectly on the plans. And when you have your shaft, you then put a structure across that's like 90 degrees to the line of the railway. You hang 2 plumb lines down it, sitting in a tub of oil or water at the bottom to damp them. And you then transfer the measurement across so you know how far it is from here to the first peg and here to the second peg. So you transfer those across. You then know what angle you want, what bearing you want to be going off, and how far you want to tunnel at that angle. And then once you've got that far, the course correction you've got to do. And what they did, they actually had course correction rulers that were put along the side of the tunnel. So you'd know that if your tunnel was trying to go around a particular radius bend, you'd have the inside ruler and the outside ruler that would be marked the same way, but actually be different lengths in and of themselves. So as long as you were sticking with the same line on both sides of it, you'd be gently going around the corner. But you've also got to worry about the vertical curves as well. It was amazing this actually worked. So the next railway to be built was the Waterloo and City, but that was, I sort of skipped over that. That was a reasonably straightforward railway to build. It also wasn't really part of the London Underground initially. It was built by the London and South Western, who ran their trains into the mainline terminus at Waterloo, who went, our trains like Paddington, all coming in quite a way out of the city where people want to work. Paddington now has a metropolitan railway bringing people through its tunnels into the city. We can't build that because we've got the Thames in the way. We'll build an underground railway. So they built their little railway, and that's why the Waterloo and City line only has 2 stations. Effectively, it's an express extension of the South West Railway coming in to get people into the City of London. Central London Railway was the next, this is almost the first proper tube. It was able to learn from the mistakes that were made by the City and South London. It built bigger tunnels that are pretty much the same size as the tube today. So we're now up to 11'6" in diameter. It didn't put stupid gradients, didn't put in stupid curves, mostly because it followed a really sensible line, pretty much east-west, all the way from Shepherd's Bush, underneath the line of Bayswater Road, Oxford Street, High Holborn, Cheapside, all the way through into the city, stopping at bang. There's a few wiggles in there. There's a few narrow bits. So if you've ever used Notting Hill Gate, Chancery Lane, or St Paul's stations, you'll realise that the platforms are slightly one above the other. And that's just because the road narrows there, and it means they can fit them in without having to buy the property either side. This is then starting to build a shaft. Not particularly tidy. You dig a hole in the ground, you build a great big ring of segments in there. You then dig out the clay underneath those segments, and you put the next bit in, and you just keep on building the shaft from top to bottom. You can see there, using a crane to try and haul one of the segments around. Some of the shafts were built by putting the ring in and then undermining it, and then building the next ring on top and using the weight of the shaft to drive itself down into the ground. It really varied on the ground conditions. There's a good point to say the reason that the London Underground is mostly on the north side of the Thames and not the south is because of the geology. South of the Thames, there's lots of water, there's lots of gravel, and it's really difficult to tunnel through. That's part of the reason. The other part of the reason is that Southern Railway had built a really comprehensive route of surface railways for commuters and put in legal objections to anyone proposing to build a tube railway south of the Thames. Most of these shafts were built at station sites. So obviously you don't want to keep buying lots and lots of properties up, knocking them down to put shafts in at random places. These days we do. We have to put in intervention points and ventilation. In those days they thought the ventilation could just work through the stations. So all we will do is build shafts at the stations, and then the shaft is used for building the line, and then when you're finished, you can then put a lift into it. The spiral staircase, you can then put a tube in and you stick a fan in the tube and pump some air in, and hopefully that will be sufficient. And if you look at some of the posters from the early 1900s, they would advertise how beautifully cool it was on the underground. Completely opposite now, because 100 years of heat has now soaked into the clay around the tunnels and keeps them too hot all year round. So how do you get started with this? Well, this is Marble Arch Station. This is a plan of it. So we've got 2 shafts for lifts, shaft for a spiral staircase. Almost a legal requirement from the start was that you had to have separate entry and exit stairways to keep the flows of passengers separate. As you can see here, you build this shaft first of all, you sink that one down, and then you build a small heading off to where you want your first platform to be. You build a little chamber here, which is big enough to erect one of those tunnelling shields in for a running tunnel, and then you just tunnel that one out to the end here, and then you start building it along the tunnelling line. It doesn't matter this is diagonal, because all the bit around it will be dismantled to create the platform later on. So once this has been done, you can enlarge this piece here, the large shield chamber, and you put in a great big tunnelling shield, about 25 feet in diameter, and you then drive that back the other way to create the platform. Sometimes they would build the running tunnel along to the right point, build the shield chamber, the large shield chamber, tunnel the platform, and then just drag the small running tunnel shield through and then start that off at the other end. Other times they would just keep running tunnels going along, and then they'd build the new tunnel around it, dismantling it as it went. The CLR was interested in automating stuff where it could, and it used this amazing thing called the Thompson excavator, which is basically like a dredger on this great big platform. So they'd be laying rails in the tunnel. You have this great big platform here and an endless chain with buckets on it that would scrape away through the front. The tunnelling shield is here. It's scraping away through the front, all of the clay. And this amazing gearing on here is an automated way of moving the barrel. So you've got a rope here that can lift it. And there's also, if you look at it the other way, it's one that can slew it from side to side. And once you set it going, it would basically work its way up and down the tunnel, just sliding across. It's almost like watching a dot matrix printer at work. It would just work its way back and forth across, scraping out all of the clay. It would dump it here, and this framework is wide enough that you can build another railway in between. So this is on broad gauge track. You build a standard gauge or even a narrow gauge track underneath that you put your spoil wagons on, and the clay would just be dropped into those, and it would then be hauled backwards and taken back to the shaft for removal. Looks like a really cool idea. Didn't work so well. It was reckoned that the rate of progress with this was the equivalent of people with pickaxes, because this broke down so often. But it was interesting nonetheless. Other interesting thing that the Central London Railway did was it had a sawtooth profile. So if you look here, we've got Shepherd's Bush Station, Holland Park, Notting Hill Gate, etc., all the way out to Banks. And all the stations, pretty much all of them, there's a bit of a hill here which makes it difficult, they're all on a hump. And this is the down line, so this is the one leading away, so this is the trains leading away from the city. Because even the tube rails refer to up and down railways, for up being as close to Bank as you could get. The trains are running this way. Trains coming towards each station would be slowed by a 1 in 60 gradient coming to the platform, and then they'd be accelerated away from the platforms on a 1 in 30 gradient. Really neat idea, because it saves you on wear and tear on brakes. It saves power for accelerating away from the station. It means that the shafts at the station are shorter, so you dig out less spoil. It means that you use less electricity to run the lifts in the shafts. It means it takes the passengers less time to go up and down with the lifts. It also means in the 1930s, when you realise that you built the platforms shorter and you'd like to have longer trains, but it's a complete pain to extend them, you've now got a piece of platform on a 1 in 30, which is against regulations. So you then end up having to dig out chunks of the tunnel roof and end up with elliptical tunnels to try and squeeze a platform in that's not too slopey. So if you've been on the Central Line recently, if you go to the end, one end of each platform you'll find is a slightly different profile to the rest of it, and you can usually see a junction, and that's what the problem is. That's an extension of about 1 car long. There's a couple of bits here you'll see. These are the sidings, one at British Museum, one at Queensway. There is actually one at Marble Arch, which for some reason isn't shown here. Sidings were always built on the level for fairly obvious reasons. You don't want stuff either accelerating itself out of your siding or into the dead end at the end of the siding. So the tunnelling shields evolved. So showing you the original great head shield. So that started off, as I said, with screw jacks and then was moved up onto hydraulic rams to push it forward. Around about 1902, they introduced the idea of a hydraulic segment erector, which is basically a huge arm in the middle that could pick up those big heavy metal segments and swing them around, particularly the ones in the roof, hold it in position while you bolted it in place. Probably saved a heck of a lot of people from crush injuries and just doing their backs in trying to lift huge pieces of heavy cast iron. Round about the same time, 1902, when this is after the Thompson excavator, there was some experimentation with, could you automate the great head shield by putting a sort of cutter on the front that would turn around? So they tried putting a motor on with an axle and then some blades on the front that would spin round, which sounds like a really neat idea, except when you're trying to go around corners, because you've cut a tunnel face that's at 90 degrees to the shield, you try and steer the shield, because it's on an axle down the middle, it just holds the blades at 90 degrees. And so the outside of the shield is starting to turn, but the cutting face isn't. And so it doesn't actually do anything other than start jamming up horribly. Someone worked out that if you put in a drive around the circumference of it instead, you avoid that problem, because you can hold the front of it completely completely transversely to the outside of it, and it will steer around. You can see big scoops fitted to these 6 blades here, or 6 arms. They will scoop the soil away and drop it onto a conveyor, or just drop it into the back of it for people to shovel away. Conveyors would seem to be the obvious thing to do, but bear in mind, early 1900s, labour is almost free. It's so cheap. It's a lot easier to throw people at the problem than it is to automate stuff. There's the back of it. So you can see all the motor stuff. There's the chute down which the spoil will be dropped. Here are your hydraulic rams around the edge to push it forward. The more rams you have, the greater finesse that you can steer it with. Yeah, and no sort of protection from moving gears and stuff like that for anyone. I've included this specially for you. It's a diagram of the track that was used in the original 3 lines that were built. So I've talked about the City and South London, which is effectively your Northern Line City branch, the Central London Railway, which is now the Central Line. The next 3 railways that were opened were the Baker Street and Waterloo, better known as the Bakerloo, the Great Northern Piccadilly and Brompton, which thank God we call the Piccadilly line because that was too much of a mouthful, and the Hampstead Tube, which is now the Charing Cross branch of the Northern Line. And they were all bought up by an American financier in the beginning years of the 20th century. They'd all been approved by Parliament, but couldn't raise the finance. This guy with the wonderful name of Charles Tyson Yerkes raised the money, mostly in the US, and was able to get these 3 railways built. And he built them to a common standard. And traditionally, in tube railways, you put the sleepers across the tunnel rings at the bottom. So you've got a curved tunnel, so the sleepers form a chord. You bolt the rails to them, and you leave the gap in between. They would put some boards along because they realised if you needed to evacuate a train in the tunnel, you wanted somewhere for people to walk. But actually, usually that was just half the width of it, and the other half, if you fell into it, well, yeah, bad luck. These 3 railways, they built proper track bed with a solid concrete piece in the middle, and then crushed granite cubes either side to give a little bit of flexibility to the track. You'll also see there's some interesting insulators. So Dalton made the insulators to hold the central negative rail and the side positive rail. This one's a really weird shape. If you ever go on the Hidden London tour of Aldwych Station, there are still some of these in place on the really disused platform, i.e. the one that was disused from 1912, not the one from 1994. Drain down the middle. You can see this is the shape of the tunnel ring here with the flange and the bolt holding it together. But otherwise, it's reasonably conventional railway track for the time. Wooden sleeper, cast iron chairs. You chuck in a wooden key and hammer that into place. You've got some cast iron coach bolts holding it down. And you've got a felt pad underneath the chair to give you a little bit of resilience against the sleeper. It's obviously moved on a lot since then. There's the man who's responsible. I think we're really good at remembering the engineering stuff, but actually less so on some of the engineers. And this is a guy called James Russell, who was an American, came across with Yerkes, Yerkes came across with 6 colleagues he brought from Chicago. And they were a rolling stock engineer. Russell, who was the engineer who designed the track and designed the power station. He had other engineers that worked on the station buildings and things like that. And I think he's a bit of an unsung hero of the underground. Yerkes gets all of the credit, partly because he has such a fantastic moustache. You'll see photos of it, really like a hedgerow on his face. But Russell was the chap who did the track, a lot of the cool engineering. So this is somewhere that still exists on the underground today. This is on the Northern Line. This is north of Borough Station, and this is where that horrible 90-degree bend on a 1 in 14 gradient was bypassed in 1900. It was only open for 10 years, and they realised they really needed something better than that. Because also, if you remember from that diagram, the railway came up, went around 90 degrees, and it stopped near the monument, but it's facing east. The obvious direction where you want to send your trains is up towards the north of the city, the Angel, King's Cross, and so on. So they bypassed the whole lot. They actually bypassed it from south of the Thames. They built new under-river tunnels, and this is the point that it branches away. So you've got the old tunnel and the new tunnel squeezed in alongside it. These tunnels were then shut off. They were laid as sidings a bit later on to store rolling stock when it wasn't needed, and then became an air raid shelter during World War II. The other interesting point here is this is the first time a step plate junction was constructed on the underground. So all of the junction tunnels that were used on the underground when they built all the lines were just built as great big cylindrical tunnels, usually the same size as the platform tunnels because you've already got a shield that big, you're already making a load of cast iron segments, you get economies of scale. And even if you just wanted a pair of points in it, you'd lay it out and you'd end up with a triangular dead space, which PWI engineers would later pile up rails, chairs, whatever else they wanted in that space. Officially, that was used for putting catch points for trains running the wrong way, but I don't think they ever really did. Because this was built around an existing railway, rather than building a great big cylindrical tunnel, which is expensive, take up more soil than you actually need, and therefore you're risking subsidence, they built it as a series of tunnels. This first tunnel here is the width of 2 running tunnels. You build a few rings of that, and then you build another one that may be 6 inches smaller, and then another one that's 6 inches smaller, and you build something that effectively is like a stepped cone, and they refer to as step plate junctions, because you risk less subsidence when you build those. And this appears to be, from research, the first time they ever built one of these. I've forgotten that. That's a picture of what one looks like. So you can see it's a series of steps moving out. So you go from 1 running tunnel to 2 running tunnels. So I've included it. This is one of the rare photos that's going to be in the next book coming out. It's not a fantastic photo, but I'm not going to apologise because I don't think this has really been seen for over 100 years. What you're looking at here is a tube tunnel, a traditional Victorian urchin-style lad with flat cap and waistcoat and work trousers and so on, and a pony. And this is building the extension to the City and South London Railway in 1905. And there's a pony in the tunnel. And that's because building tube railways was seen as a mining technique. You know, we build mines into hillsides and down shafts and spread out to get the coal. How do we do that? Well, we drop ponies down there and we build stables down underneath, and the ponies live their lives down there, and they're the motive force for moving all the wagons around. Building a tube railway, well, you're just mining clay. You don't want the clay, you want the space left by the clay. But you might as well use ponies. There's no stables down there. You just lower them down at the beginning of each shift and then lift them out again. You know, you need a couple of straps underneath them and pulling them up and down on the cranes. But there are diagrams showing ponies being used. This is the first and only photo I've ever found showing, you know, incontrovertible proof of there is a tube tunnel with a pony. It was used to pull the clay spoil wagons back out. You can see one of the wagons there, slightly dubious looking fellow with a dodgy moustache lurking at the side there. Yeah, but a little bit of history there. So I mentioned that the City and South London Railway was built with tunnels 10 feet 2 in diameter, so really tiny. It's not quite the case. Some of it was built with 10 foot 2. So the piece that I mentioned, the first bit from King William Street in the city down to Elephant and Castle was built at 10 foot 2. The extension that they built in parallel with the first piece before it even opened as a line down to Stockwell was built to 10 foot 6. But this was still too small. All the other railways were now at somewhere between 11 foot 6 and 11 foot 10. And this made it a complete anomaly. By 1913, all the railways were under the control of the same company, with the exception of the Metropolitan Railway and another railway, which is actually part of British Rail or Northern Network Rail these days, the Great Northern City Railway out of Moorgate. All the rest of them are now run by the same company, and they're running the City and South London Railway with these tiny little trains where you're going to have to go for custom rolling stock build if you ever want to change anything on there, which is always going to be expensive. And you can't fit so many people through it. So what do? You make it bigger. So in 1913, they got permission to enlarge it. Then the First World War came along, so they didn't do anything. And it took until 1922 before they got enough money to start enlarging it. And so part of it was closed down, and they just dismantled it ring by ring, dug out the clay around it and put bigger rings in. Part of it, so from Moorgate down to Stockwell, they decided they'd keep the trains running while they enlarged it. So remember your Great Head Shield, the hole in the middle of it, you make it big enough for trains to go through. You leave it in place during the day, and then at night, the trains are off the track. You send someone, or a team of people down, you unbolt the rails that are going through the middle of the shield, you remove all the signalling cables and all your compressed air pipes and things at the side, reroute them round. You then drive the shield, dismantle the tunnel in front of it, drive the shield forward maybe 2, 3, 4 rings, rebolt the tunnel back together afterwards behind it, and then quickly relay the track, connect all your signalling cables, pop your air mains back in. I mean, it's only a few minutes work to put away. Now, I said you rebuild the tunnel, so you've now taken out the tunnel segments that perhaps for a tunnel 10 feet to 2 in diameter, you've now got a tunnel 11 foot 8 in diameter. Do you take in a complete ring of new tunnelling segments? Of course you don't. What you do is you take in a handful of small tunnelling segments, and you end up with a really weird shaped tunnel like this, where, yeah, it's a, yeah, daisy shaped, or slightly odd like that. This worked tolerably well for a short time. So near Stockwell, the ground's horrible. It took the original company longer than expected to build the tunnel to reach Stockwell station because of the amount of water and gravel in the ground. And they ended up having to seal the tunnel off and pressurise it with compressed air and get the work done. And the compressed air would hold the water back. In order to do this work, they built 2 new crossover tunnels between Oval and Stockwell so they could use single line working and close off sections of the tunnel at a time, compress them, enlarge them, and then reopen them and reroute the single line working. It worked for about a month, possibly not even quite a month, in fact. The tunnelling shield, which is moving along with the track and the trains going through it, obviously not quite at the same time. At the end of each night, they go and prop the roof up with some boards and let the trains go through. Trains are big, heavy, vibrating things. The boards shake loose one day. The train is running through, and there's a bang from the back of the train, and the board is knocked out, and the back end of the train is covered with gravel pouring down with a lot of water. The driver has the presence of mind to accelerate the train through, stop, check with the conductor, what's going on, looks like the tunnel's collapsed, right, let's move on to the next station then, that might be safer. But they then realise that maybe this wasn't the best idea, close the whole line down for rebuilding. Meanwhile, on the surface, before they even closed the line down really, on the surface, a few minutes later, with all this gravel pouring into the tunnel, a void forms underneath the road, because it's obviously following the roads. The gas main that's in the void collapses under its own weight and ignites. There's a huge explosion which blows the road surface up. It also blows the water main up, which then puts the flames out in the hole. And then the police come along and go, whoops, that doesn't look great. We better close all this up and find out what's happened here. The railway was then closed for about a year while they just did a complete rebuild of the whole thing. Got all the tunnels sorted out, and they now have a railway which is, it says there, 10 foot 6 enlarged to 11 foot 8 1/4. You can now put the same rolling stock down, and they could also join. See what the next slide is. Otherwise, I end up talking about the slide in advance. No, didn't. You then join this railway from Euston. You extend it through to Camden Town, where the Hampstead Tube is. From Charing Cross, which is the southern end of the Hampstead Tube, you drive it down to Kennington, where the City and South London Railway is, and suddenly you've got the Northern Line that we know today, pretty much, apart from some of the bits in the north. As far as the tube tunnels go, you've got the deep level tube. You've also got the complexity of having a route that has one southern route, 2 branches through central London that merge and then demerge again to form 2 branches in the north. If you look at the history of it, they also wanted to build another junction tunnel with the Bakerloo line underneath Waterloo Station, so they'd have a 3rd branch of it. And then they tried to do even more in the Second World War that would add greater complexity. Just as well they didn't. Also in the 20s, they wanted to rebuild a lot of the stations with escalators, because lifts move a lot of people in one go. If you turn up at the right time in a station and the lift is about to go, it's quite quick to get down to the platform. If you turn up just after the lift's gone, it's really quite slow. If you've got escalators, you can move people down on a constant rate. So this is a picture, what's known for some underground people as stomach diagram, just an axonometric or isometric drawing. This is how Oxford Circus was rebuilt. So we have the Bakerloo line running here, Central line running it crossways. This is the building for the Central London Railway. This is the building for the Bakerloo. Separate companies, remember, so they couldn't use the same station building. You'd have 2 sets of lifts going down to the bottom. They did have connecting passageways down below with tiny little ticket offices in them, because if you changed trains from one line to the other, you'd have to rebook onto your new line. But now they've had to put in the escalators, and you're starting to see the complexity that Oxford Circus exhibits to this day. So Oxford Circus was rebuilt partly before it even opened, because the original layout of it, as planned, fell foul of Board of Trade regulations, who went, this is just a complete mess. We need some changes. So they ended up having to fill in tunnels they'd already built and make a few different connections. This now became even more complicated. The first two escalators were put into the Bakerloo line, and they ended up having to reroute some of the passages round and build avoiding passages. And then they put in the escalators a little later down to the central line, where they couldn't drop them in to the normal position, which would be between the platforms. So they've ended up above the platform, in going out into an escalator chamber where people then go sideways in to stairs that lead down. One of the things that people who aren't familiar with London often wonder is, why do we have so many stations where the lifts and the escalators don't go down to platform level, but go down to a level where you've then got to walk along a passageway and downstairs to the platforms? And this is again because of the railways running under the street. If the railway runs under the street, you can't drop a lift down to the platforms. You've got to drop a lift down at the side and then make people move sideways, and then you're not going to put another lift in, certainly not in those days. So you always have to have some stairs. And a lot of that was reused with the escalators being put in as well. So this is now even more complicated because we now have the Victoria line running either side here. We have far more escalators. We have the ticket hall underneath Oxford Circus. It's an absolute warren under there. So the Victoria line didn't use great head shields mostly. There are some bits, like under Green Park, I think, was built using great head shields because it's wet and gunky under there. They developed a new piece of technology. This was developed by Kinnair Moody, the drum digger. So this is a great big rotating device. But crudely, it's like having two tin cans, one slightly larger than the other, that interlock, and one of them contains motors that spins the other one round very slowly, and it's got lots and lots of really hard cutting teeth on the edge. This is effectively a forerunner of today's tunnel boring machines. And it's got the hydraulics at the back that will push it forward. It even has a sort of trailer type element at the back that will pull through equipment for building the tunnel behind it. This is a really interesting picture because you very rarely see. You either see these in the factory all looking pristine, or you'll see the front end of it because it's in the tunnel, or you'll more usually see the back end of it because it's in the tunnel and the front end is buried in the clay. What's happened here is we have the running tunnel. This has come through the running tunnel, broken through the head wall of the running tunnel into a station platform that's already been built, and this is now being pulled on skids through to start building the running tunnel at the other end. There's some quite cool kit there. And as with a lot of this technology, these days, if you look at who builds tunnel boring machines, you've got Herrenknecht in Germany, you've got Kawasaki in Japan, you've got Lovett in Canada, there's Robbins, American company who builds them. There aren't actually any British companies who build them, but the technology is all British. We designed and developed the technology and then didn't invest in it, and other countries have taken the lead in all of it.
Usual story.
Yeah, usual story. Sorry, squashed my writing a bit there. The tunnel lining for the Victoria line is not the same as on the other lines. So they wanted to make some changes. In the Second World War, we started using concrete tunnel linings because cast iron was all being used to make boats and bombs and things like that. So London Underground pioneered the use of concrete running tunnels, and a load of the central line extensions that were built during the Second World War used concrete tunnel linings. The Victoria line used a new type of concrete tunnel lining, which had these curved ends on them. And the idea here was that rather than fitting them together and bolting them like the concrete that was used in the war, which is big, heavy concrete linings that needed huge bolts holding the flanges together, there's no flanges inside here. You just press these out against the clay, and then the clay presses back and locks it all together using these convex and concave ends. And because you've got fairly consistent pressure from the clay, it just holds the tunnel into position. It also means that you can precast a lot of the stuff like the invert for the track bed into those. And then you've got, if you look at the cross section through here, you've got pockets in there that you can, the tunnel machine can hook onto to jack itself forward and to help press it all out. Also means that because this is far thinner than even the cast iron linings, you build a smaller tunnel through the clay to get the same size running tunnel inside. Although that said, the internal diameter of the Victoria line is about 12'6" rather than 12 foot or even slightly less on the other lines. They deliberately made it slightly bigger. And if you travel on the Victoria line in the last 10 years, the newer trains that are running on it at the moment are actually bigger than the old ones because they've taken advantage of that extra space in the tube. With a disadvantage, it means they can never transfer them off the line via the connections onto the Piccadilly line that exist at Finsbury Park because they're too big to fit through the Piccadilly line tunnels. So the trains have to be brought in and brought out on low loaders. That's what it looks like inside. So you have rather more segments making up each tunnel ring. The brackets screw onto cast pieces in the concrete, or holes that are cast into the concrete with like screw fittings and things. So everything's tucked in as neatly as possible. Some of these also have the dubious effect. They put in a shelf to try and trap the noise down coming from the rails and the wheels down below train level. Some of these used a heck of a lot of asbestos, which has now been removed, but it's a bit of an expensive failed experiment. This is the tunnelling breakthrough at Heathrow Airport. So when the Piccadilly line was extended in the 1970s to Heathrow Airport, rather than using a drum digger, it wasn't going to be a huge, not building a huge amount of line. So it was only 2 stations. It was running from Hounslow West through Hatton Cross into terminals 1, 2, and 3. No point building a drum digger for that, particularly given that the bit between Hounslow West and Hatton Cross was built as cut and cover. So you're only building a kilometre or so of tunnel. So a TBM or even a drum digger is just not worth it. So they used effectively a great head shield, but it's using a road header. So it's one of the bit of equipment that you use in coal mining. So effectively, it's fitted into the shield, it can be swung around, and it's just got a spinning spiky thing, to use a technical term, that rips the clay out, and people then shovel it out from the back and take it away. Off the top of my head, I think one of the tunnels was built using a DOSCO road header, and the other one was used some technology from Anderson Mavor, or Mavor Anderson. So trying out different technologies. They used it, they're trying to do a bit of experimentation as they built it as well. But it's interesting, there's still the innovation. They wanted to see what other technologies are out there for making holes in the ground that could be adapted for use on the underground. So rather than having to build brand new pieces of kit all the time. The Jubilee Line extension was the first instance of proper tunnel boring machine technology being used for the London Underground. And I can't remember which station that was at. Funny feeling that might be North Greenwich. It's one of the great big box stations where they dug just a simply enormous hole in the ground. I mean, the station at North Greenwich is big enough to lower the entire tower from Canary Wharf in on its side. It's terrifyingly big. It's actually got a provision for a junction at the end of it in case the Jubilee Line was ever extended to Thamesmead. So it's longer than it actually needs to be for the station. TBMs that were built in segments. So this is the, I think, front segment. That gets lowered in, and then you fit other pieces in behind it. So you've got the hydraulic drive for it. You've got facilities for the workers on board now. So they've got toilets on board, they've got a kitchen on board, they've got a mess room on board. Because the idea is you're down there for 12 hours, you're driving the tunnel through. It means you're not expecting your staff to sit there for 12 hours driving a tunnel boring machine, which probably isn't the most exciting driving experience. Although, completely aside, you can actually buy a tunnel boring machine simulator game for. That's really odd. But anyway, so the staff on there can be driving the machine, and they can go back and take swap over, take a break, go to the loo, get themselves a drink. There's also a lot of stuff on the back of these. It's only when you start thinking, how do these work, that you realise they've got to have a huge extension reel on the back. Because as they're moving forward, you've got to be laying out the power cable, otherwise the plug's going to come out of the socket at the other end. You've also got all the pipes bringing in a lot. So a lot of these in South London use what's called a bentonite shield. So because you're cutting through things like chalk, and it's not so much clay, but it's the gravels, you need to hold the face up. So rather than making the miners work under compressed air, which is bad from a medical perspective, you pressurise the front piece. A special type of clay called bentonite that will support the weight of the clay while it's being cut. And the clay falls into it, and you just pump the whole lot back as a slurry. You pump it through a load of pipes to the surface to a machine that separates it all out, and then you pump the bentonite back and go and dump the clay somewhere. So you've got a huge amount of pipe work, cabling, and all sorts of stuff being dragged along. And every so often you do need to stop the machine and plug a new reel in. It's probably more complicated than that because these don't run on like 230 volts. They are big. I think some of them are like kilovolt type power supplies to run them. There's a cross section. This is one of the ones that was used to build Crossrail. This is Heron Knecht, the German manufacturer. So this is the pressurized chamber at the front. The teeth break away the clay, falls into this chamber here. This screw conveyor then pulls the clay up, extrudes it out of the back onto a conveyor system that carries it all the way through the machine to the back. Further back, so down here, this is about 100 metres of trailer that's being pulled behind it with all the staff welfare stuff. There's also a magazine on there that holds a big stack of all the tunnelling segments, the tunnel ring segments that are needed, and all the equipment to erect it. So we've moved on from people manhandling 200 kiloweight cast iron, 200 hundredweight cast iron segments. We've moved away from a hydraulic segment erector. This is just picking the machine, the big concrete segments up using vacuum technology. So just put some vacuum suckers onto each piece of concrete, lifts them up, swings them into position, pops them into place, bolts it all together, and it's completely automated. There's usually something down here to crush rocks, which depends. You spec these machines out for the kind of ground that you're going through. What you don't want is a big rock jamming this. So if you're going to be going through places that have got big rocks in it, you put something in that'll smash the rocks up first before you tow them out. What else is there to say about that? Yep, hydraulic rams are here. So you can see them pushing against the last piece of the tunnel that's been built. And what happens is the tunnel segments are actually brought through underneath all the rest of the machine to this point. And this bit here is effectively the rotating bit, the arm that will pick up these segments, swing them round all the conveyor belt piece and fit them in. And they're absolute masterpieces of engineering. As I said, that was used to build Crossrail. Similar machine was used to build the Battersea extension on the Northern Line. It depends on, you've got to have a good length of tunnel to build in order to justify paying for a tunnel boring machine. These are about £10 million a piece. But the great thing is once you've finished with them, the manufacturer will normally buy them back and recycle some of the components. So on Crossrail, the outer bit, the skin, when they reached Farringdon, there wasn't the space to take it all apart. And so they just built the running, they take out the cutting bit, they take out all the expensive technology, but the metal skin is just left, and that's entombed behind the running tunnels at Farringdon on both the stations. There are other bits. A century ago, they still did that with some of the Great Head shields. There are bits of those stuck behind tunnels for archaeologists to find in centuries' time. So I mentioned the Battersea extension a few times. I was a bit cheeky. So Ferrovial, who built this, contacted me after I'd written my last book and said, can we interview you for a podcast? Can we do a series of podcasts about interesting projects we've been involved in? I think, yeah, of course, I love talking about this stuff, as you've probably noticed. I went and had a good chat to them. I went, we're really sorry we can't pay you for this. And I went, I don't want any money, but can I have a tour of your tunnels, please? They went, oh, yeah, that's fine. I mean, you can't buy experience stuff. You may well go down tunnels and things in the course of your job, but I don't. I like doing that sort of thing. So I spent half a day with one of their engineers down in the extension. This is the point. It's quite a nice photo here because of what it's showing. So south of Kennington, there's a loop on the Northern Line. So trains coming in from the Charing Cross branch can either run onto the Morden branch to South London, or they can run all the way around the loop, 180 degrees, to head back towards Charing Cross. That's a Northern Line train that's running around the loop. This tunnel here around it is a step plate junction that's been built subsequently, almost 100 years later, around that. And I'm standing in the tunnel. This is the northbound tunnel from Battersea and Nine Elms, looking into here. Can't go beyond that barrier because that's live railway beyond. There's no worry here because there's no electric tracks in place. You can see it's all slab track that's been laid. This piece of the tunnel here, there's not really much you can see in the way of concrete tunnel lining segments in here. It's quite smooth, and that's because the tunnel boring machine has stopped short, been dismantled, and this has all been hand mined out to join it in to ensure there's no disruption to the step plate junction and the live railway tunnel. And as they hand mine it, they mine it a metre at a time and then spray the whole thing with concrete to hold it back. So the clay is actually exposed now, but only for a very, very brief time. And the spraying is actually done robotically. So it's a machine that's driven from almost like a games console, and they can drive the thing forward and they'll spray the concrete round, and then they put a waterproof membrane in and then spray a new concrete lining on to keep it neat. And then temporary lighting goes in, the track gets laid, and then finally you do all the rest of the fitting out that's needed. So that's basically what it looks like where you join these things on, though. And I think that's it. That was a bit of a whistle-stop tour and how they built the deep level tubes. I'm not trying to flog my book because it's out now, out of print. So you can find it on eBay and secondhand bookshops and things like that if you're interested and you feel you haven't heard enough from me this evening. That is sort of the civil engineering history of the London Underground right from Brunel's Under River Tunnel all the way up to Crossrail. It's lots of technical detail because I like technical detail. But that's it. So thank you very much.
Any questions? Spring-ended sleepers. Not the greatest invention.
No, it wasn't, was it?
No. It was one of the things that the PPP contractors were incentivized to get rid of. Depressing that, given when they were put in, it was PPP, they were still being incentivized to get rid of them in, around 2000. Yeah.
Yeah,
it couldn't have been that bad then, till if they lasted 100 years.
Well, of course, they were new, but the principle wasn't great.
Well, I mean, all the original track was flat bottom rail, so it was bullhead rail.
Enough of it still is.
And there's a heck of a lot still out there, and there's some interesting transition points now into the flat bottom stuff they've been putting in as well. There was all sorts of interesting stuff in the early days. There was longitudinal sleepers supporting some of it. There were some bits of it built with some odd-shaped rails. I don't think there's any sort of fish belly rail used on it, thankfully. It was pretty much all bullhead that was put in at the time. They did some interesting experiments with manganese additives to the rails, particularly relevant as we are here, sort of almost between Bank and Liverpool Street on the Central Line. When that was extended in 1912, the entire thing was laid with manganese steel rail, because at the other end of the line, near Shepherd's Bush, there's a very sharp curve, and they found that the rails would wear out in 4 to 6 months on that curve. And that was the depot connection, so it wasn't taking particularly intensive traffic until 1908, when they then opened it up for passenger traffic. So they laid the entirety of the extension, because this is a city, it's lots of narrow, windy streets. So the extension from Bank to Liverpool Street, there is not a single section of straight track on it at all. It just winds, wiggles all the way along. The whole thing was laid with manganese steel rails, which were quite innovative at the time.
Did we have any gauging issues with the early railways, sort of fairly tight tunnels?
So in terms of track gauging, I don't think so. There've been interesting issues in terms of the kinematic envelope within the tunnels.
Yeah.
So on the Central Line, I pointed out a couple of sidings. There's one at Queensway. Those sidings are really weird because they weren't just reversing sidings, they were a combination reversing siding and crossover. So I think it was a trailing crossover that had a reversing siding coming off from the middle of it. So it might have even had a facing connection as well. There's definitely a scissors crossover linked with a reversing siding, and they squeezed it into the shortest length of tunnel they possibly could to minimise costs and subsidence. And it was really, really short radius curves. And when they changed the rolling stock in the 60s, they would encounter problems because just the angle between the trains, they actually started finding that where the trains, I think there were 2 4-car units of trains, and at the junction between the 2 of them, they would actually come into collision. They were breaking the tail lights on the trains. And they weren't sure why there were broken tail lights on their trains. It was only when someone found the broken glass in the siding, or in this junction, they went, oh, probably here then. And at that point, they started reducing the use of that. Generally speaking, the tunnels are pretty good for the kinematic envelope. It's really tight, but because the track is designed to be as rigid as possible, the trains don't move too much in there. It'd be fairly bad if they did.
Did you include anything about the relining of the Northern Line around Angel due to the erosion of the original segments from acidic groundwater?
So that's in the book. It's fascinating. It's down at Old Street. Yeah. So another groundwater problem. The soil down near Old Street Station contains lenses of sand that contain iron pyrite and water, which is absolutely fine as long as you leave it be. If you let air get into it, for example, by pushing a tube tunnel through, you then get a chemical reaction that forms really quite concentrated sulfuric acid. which isn't a problem unless you build your tunnel out of something like cast iron, which will then dissolve. And so by the 1960s, they found that the tunnel through there was getting cracks in it. And when they looked at it, they found that it was being dissolved from the outside. And it was actually the sulfuric acid was corroding the tunnel and reacting with the cement grout behind it, which was causing the formation, I think, of gypsum crystals, which is calcium sulfate, which are larger, they're lower density, but they're larger. So they were putting pressure on the outside of the tunnel, which was then weakened and cracking. So they ended up strapping the tunnel together with a whole load of steel bands inside it, which worked for a bit until it didn't. They then sank boreholes from the surface and pumped in as much sodium hydroxide as they could to try and neutralize the acid, which is fine if you've got a small amount of acid, you know how much acid, but it wasn't and they didn't. So in the 1990s, they used the fact that there was an old reversing siding that was disused since the rebuilding in the 1920s. They borrowed the playground of a school nearby, sank a shaft down to below the running tunnels, out to beneath them, a vertical access shaft into the disused siding, broke out from that into the running tunnels, built a new shield chamber, bored them all at a rather larger diameter, and then relined the whole tunnels with stainless steel segments, which are just eye-wateringly expensive to build, probably beautifully shiny. But that stopped the problem. And they obviously sealed them very, very well together so you don't get anything coming through into the tunnels. But yeah, that was a really fascinating piece of work.
At one stage, you could go, before it was relined, you could go down and pull clay out of the back of some of the segments.
Yeah. Although, probably with gloves on, given the sulfuric acid in there.
Of course.
Not for this session, but there's it's a cut and cover. I would like to know the Barbican, where they rerouted Barbican.
Yep.
And they put it all on a floating. Probably not for now, because it's done deep.
That was one of the first uses of floating track on the underground, I think.
Yeah.
So yeah, so where the Barbican estate is, that was completely bombed. There's absolutely nothing left after the war. And the Metropolitan Railway used to take quite a long curve around it. And so to build the Barbican, they rerouted it on a far shorter alignment between Barbican and Moorgate stations. And they built all of that in tunnel and then built the Barbican estate over the top. And because people are living there, all that track was laid as floating track with sort of rubber boots to try and absorb the vibration. I'm not sure it's working so well now. I think
they've
it's
got plenty of noise complaints.
Yeah. And the
You
tunnel,
can still go down and see it though, but
Yeah.
not many people.
the tunnel has got extra lining around it that also tries to suppress sound, but I think that's also life expired now. Crossrail, where that's gone underneath, has put some really clever floating track construction in. Even to the point, I think they've used a special high density concrete in the track bed that's made using magnetite powder in it to just make it hugely dense, because that way the vibration, the frequencies that will come out from the tunnels are modified so it won't annoy the residents. Yeah, it's really clever stuff. So, question from over here as well?
I was just wondering if there was any plans for a sequel, perhaps abroad. Have you done anything in say like the Paris Metro? Or
I have far too much material on the Paris Metro at home, and I would love to write a book on it. The trouble is, I keep being asked to write books on the London Underground, and I've also got to try and hold a job down. So yeah, that's really fascinating as well. I don't know much about the track on the Metro though, but quite a lot about the engineering history, because I happen to have an atlas that basically shows you how to build half the Paris Metro. It's all the detailed engineering drawings of 3 of the lines. This huge, great booklet, huge plates showing you how every station, every curve, and every bit of tunnel, and everything was built. Brilliant, but I have a very understanding wife. Yeah.
Did the book include the realignment of the Piccadilly line at Finchley Park due to the Victoria?
Yes, yeah, all that's covered in there, and all the diversion tunnels and the rebuilding of bits of the Great Northern City. So building new tunnels to hold mainline sized trains to go through, because they would ultimately be reused by British Rail, as was. Yeah, that's quite an interesting challenge as well.
Thanks.
Any question?
Just put something in on the Crossrail under the Barbican area. It's actually confused us as the independent assessors, because we'd never come across slab track that was less stiff than ballasted track before. Normally, when you're doing transitions from slab track, the slab track's rigid and then you get the ballasted track. But because of the nature of the track in the area, it's actually the other way around. And that was a bit disconcerting. We wasn't, we initially we said, this can't be right. It can't be less stiff, but it is.
That's right. In fact, you just reminded me, because in fact, it's floating slab track. They built a concrete raft that has a slab track on it that is then supported on rubber bearers into the tunnels. So the entire slab will absorb the vibrations from the trains.
Yeah, it's actually less stiff than ballasted track. It's surreal.
No more questions? I don't think there is any other question online.
Yes. Well, thank you, Anthony. That was a really interesting talk. It's really interesting. A few things, some really good stories. I'll take my back off the camera. Really interesting talk. So thank you very much. It's really interesting to hear the enthusiasts' kind of version rather than engineers' version. So very interesting from my point of view. Some really interesting stories, and you're a very difficult man to follow. So we thank Antony in the usual way.
Thank you very much. Thank you. Are we gonna go to
Well, I am.
we know where?
The Grapes. So turn right out of the building, left into Lime Street, and it's down there on the right.
Yeah, so we've all heard Mike.
Follow Mike.
Yeah, we're gonna follow him. Go too far and have a drink with you, and we're gonna go home. Everyone's welcome to join us. Thank you very much for coming today.
Thank you.
Right.